So good morning, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those who are joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. Right now, we're joined by 6 classes from across North America, so I'm going to give them a chance to do a bit of a shout-out. We've got Miss Leany's grade 4 through 6s in Seaforth, Ontario. Awesome. We've got Mr. LeBeau's grade 8s in North Palm Beach, Florida.
Hello.
Hey. We've got Miss Godard's grade 7s in Brampton, Ontario. Hey, guys. We've got Miss Huff's group, which will be joining us soon, grade 8s in Mashpee, Massachusetts. We've got Miss Goddard's 4 through 6s in Stratford, Ontario. Hey, guys. And we've got Miss Russell's grade 8s in Brampton, Ontario. Hi, guys. Their video's off, their mic's off, but they're there and they're excited. Of course, the reason you guys are all here today is for our speaker. So we are joined live by Dr. Caden, 2 kilometers underground in SNOLAB. So SNOLAB is one of the most unique facilities in the entire world. They study some of the most mysterious and interesting phenomena in the universe, but deep underground, which I'm sure we'll find out from Dr. Caden exactly why they do that. It's our first ever hangout with SNOLAB. We're so thrilled to have them. And Dr. Caden, thank you so much, and take it away.
Hi, everyone. Yes, so I am Dr. Erica Caden. I am a research physicist here at SNOLAB. I put together a couple of slides to tell you about what SNOLAB is and what we do here and why we do it here. I can take you around and show you some of the facility where I am right now. So right now, as Jesse said, I am 2 kilometers. That's 1.25 miles underground in a facility. But let me get to the slides to show you a little bit better. Let me screen share. And okay, here we go. Can everyone see?
Yep.
So this is me doing science here on my experiment at SNOLAB. So this is the surface facility of SNOLAB. We are in Sudbury, Ontario. So that's about 4 hours north of Toronto, where the pin is on the map. This is a picture of our surface building. It is winter now, but it's not winter always. But the facility where I am in right now is underground. So this is a picture of the mine. So SNOLAB is in an active mine, a nickel mine. There's a lot of nickel in Northern Ontario here. So this is one part of the vein of the deposit of nickel ore is all of the red area. And the SNOLAB, if you go down the number 9 shaft, which is the big elevator tunnel down 2 kilometers to 6,800 feet, and then another 1.5 kilometers walking through the drift is the technical term, you get to SNOLAB. So this is, excuse me, we are over 3.5 times deeper than the tallest structure in the Western Hemisphere, which is the CN Tower. So we're deep here. Here is a kind of a picture of the layout of the lab. It is an underground facility to study particle astrophysics is our technical term. But really what we're doing is studying the stars and the space and the heavens from deep underground. The facility is approximately the size of a shopping mall. So 5,000 square meters or 54,000 square feet of space. And that's including 3 large caverns. I don't know if you can see my mouse. 3 large caverns for very large experiments looking for neutrinos and dark matter. So this is what we do here at SNOLAB is neutrinos and dark matter studies. So neutrinos aren't just cute little plushies that you can get from the particlezoo.net. Neutrinos are fundamental particles, similar to electrons, but different in that they're very, very hard to detect. So neutrinos come from Radioactive reactions like fusion in the sun or fission in nuclear power stations, or just normal beta decays, rock decays, decays of normal elements that happen all the time. Neutrinos are produced in these reactions. So they come from everywhere, but they are hard to detect, and they're different than electrons and other particles that we know about in other ways. But studying neutrinos can help us answer questions about the world, such as why is the Earth so warm? How do elements form in the sun? How do stars explode? And how are we even here at all? Why was, after the Big Bang, why is there more matter in the world? How are we here? So this is a picture of the experiment that I work on called SNO+. This was during its original construction days when it was called the SNO experiment for the Sudbury Neutrino Observatory. You can see in the bottom right-hand side, the small people. This is for scale. This outside structure is 60 feet or 18 meters in diameter. This sphere is holding lots of light sensors. So these are more sensitive than the human eye, all of our light detectors. And each white dot on the back is one of them. And we have 9,500 of them kind of all looking inside on the sphere. This cavern that the detector is in is 21 meters wide and 30 meters tall. So about 70 by 100 feet in a barrel shape. So this is what it looks like on the inside now that we're all filled with water. Each dot that you see here is the inside of one of those photo detectors. You can see the edge of the acrylic vessel. So this is an inner sphere that is 12 meters in diameter that holds our detector liquid. So for the original SNO experiment, that was heavy water that had an extra neutron in the nucleus of the hydrogen atom. That let the original SNO experiment see neutrinos from the sun and solve this problem that we had of not understanding exactly or not being sure that we understood how the sun worked. So now we're using right now regular water and soon a mineral oil to detect neutrinos and antineutrinos and answer some other questions about them. But that's not all we study here at SNOLAB. There are many experiments looking for dark matter. Here are two of them. This is called Deep 3600, and this one is called PICO. So dark matter is even more kind of esoteric or difficult to understand than neutrinos. But we kind of think of it as the invisible space glue that holds galaxies together and keeps whole galaxy clusters from spinning apart as they go through space. So we haven't actually observed the dark matter particle yet. But this is what keeps scientists like me on our toes and working on projects here at SNOLAB. So that's it. That's what I have to begin with. I guess I can stop sharing my screen. So I can walk you around a little bit here. I can answer some of your questions if you want to start.
Yeah, why don't we walk around a little bit? One of our class just joined us, and that's entirely my fault. So Ms. Easton's class, I apologize. So just, yeah, showing us a little bit around the facility would be amazing, and then we'll just dive right in with questions from everyone.
Okay.
A great presentation. Thank you so much.
Thank you. So we are in what is called the control room. So we have, I'm just going to carry my laptop around and try not to trip on the cords. We have a bunch of computers that we use to actually run the experiment right now. I'm working with a bunch of other folks behind me who are working on other parts of the project. So in particle physics, we have really big groups of people working on really big experiments because they are the answers that we're looking for are to very complicated questions. And so that takes a lot of people working together. So that's what we have right now. So I don't know if you can tell, you can see the walls are really bumpy. This is from being just dug out and mined and blasted out of rock and then sprayed with concrete to help keep it secure. I am going to back onto our deck. So now you can kind of see how far the cord stretches. There's some electronics behind me. The green blinky lights, those are the electronics that power all of our photo sensors and keep things running. The white room behind me is the center of our detector goes up through there, so it has to be extra, extra clean. So the reason that we're underground is for to use the earth itself to shield from background radiation that would make our experiments impossible to do. We're looking for itty bitty flashes of light, and there's lots of things that can make itty bitty flashes of light. So we have to try and shield them all away before, so we can find the ones we're looking for. So the 2 kilometers of earth shields most other things that can cause these flashes of light. But we're also in what's called a clean lab. So that means it's essentially like an operating room. It's that level of dust-free. So you'll see that I have a hairnet underneath my hard hat, and I'm in these lovely blue coveralls that everyone is wearing. So to come to work every day underground, you have to take a shower after you've walked 1.5 kilometers through the mine just before you can come into the lab. And every piece that we bring in has to be showered or cleaned or wiped down as well. So that is to help not bring in anything else that causes radioactivity into the lab. Yeah.
That's great. We can dive right in with questions.
Yeah.
Awesome. Thank you so much. All right. Well, we'll start with Miss Huff's. Miss Huff's class isn't in yet. They're coming in 4 minutes. Let's start with Miss Gerhari's class. You guys have a question? Go right ahead. Any questions, guys? In Brampton class number 1? If you do, you can come right up to the computer, guys. Yep, take your time. Your mic is really, really low, by the way, so we can barely hear you. So do come really close to the computer, okay?
So, like, how do you transmit us to us when you said there's no Wi-Fi?
Oh, no, we have Wi-Fi. So I just happen to be using a cable now because sometimes you know how Wi-Fi can be. But we do have internet here, and internet, the Ethernet is how we transmit all of our data up to surface. We have optical cables or optical fibers that we use to transmit data from the lab up to our computers on surface.
I love how the first question revolves around Wi-Fi.
It's very important. It was amazing when we got Wi-Fi in the lab.
Cool. Let's go to Miss Godard's group next. If you guys have a question, come on up. So for the kids that are pro at demuting their mic, actually, we should be good to demute your mic. But yeah. If there are any problems, it's probably my computer now. Just doing weird things. So Miss Godard's group. You guys good for a question? We can come back in a minute. We'll come back in a minute. Let's go to Miss Lee's class. If you guys have a question, go for it.
Yes, we're unmuted. Sure.
There you go. You're good.
Erica, where did you go to school, and what did you have to do in school to get here?
I am from the States. I grew up in New Jersey, and I went to graduate to university and then to graduate school at Drexel University in Philadelphia. And then I came up to do what's called a postdoc, which is your first job after you finish your PhD at Laurentian University, which is in Sudbury, because I wanted to work at SNOLAB. I thought the project that I'm working on now, SNO Plus, was so cool and had the opportunity and the possibility to do so many interesting studies of neutrinos in different ways that I came right up here, and then I got a job at the lab as a research scientist, which is kind of like my dream job to be a scientist, that I just get to do science and work underground and talk to people about science all day.
Very cool. Good for you. And good question. Let's go to Mr. LeBeau's group.
Go ahead, Will. You can just say.
Oh, what's the advantage of conducting science underground?
So that's a great question. So we do science deep underground to shield all of our sensitive detectors from what's called cosmic rays. So these are charged particles that just create muons, which are other charged particles that make a lot of light in our detector. So it's akin to if you're listening to a symphony and you're trying to hear someone drop a pin on the ground, is the relative intensity to how much electromagnetic noise there is from particles in our detectors. Would they be on surface versus underground? Underground, we can hear that pin drop. So that's why 2 kilometers underground is a really great depth to shield out as much as possible, but still have this facility in an already existing mine that we didn't have to blast out all of the space that it was already existing here. There are a number of underground labs kind of around the world. There's one in China, there's one in Japan, there's one in South Dakota. But we're the only lab that operates the entire facility as a clean room, so that everyone walks in and dresses like me and wears hairnets, and the entire facility is operated in this way.
Very cool. All right, let's go to Miss Russell's group. So you guys just need to demute your own mic. So come to the front if anyone has a question, or if all of you have a question, it looks like. Yeah, just demute that mic and you'll be good to go, okay? Not yet, guys. So yeah, someone needs to come up to the computer, go to the top of the screen, little microphone. There you go, you're good.
Good job, baby. Now you so, how do you guys get oxygen when you're 2 kilometers underground?
So that's a good question. We have air flow and air handlers that pull air through the tunnels that we walk through. So it's just the same air as on surface, and is pulled through and cleaned. So air is dusty because it's come through the same dusty, dirty mine tunnels that we have just walked through. So there's a big effort to clean the air and put it through filters before it comes into the lab, so that we're not making our clean area dirty.
Excellent question. All right, let's go to Miss Easton's group in Woodstock, Ontario, grade 12 guys. If you guys have any questions, again, come on up, demute your mic, little mic symbol top your screen, and you'll be good to go. And I'll let you know. Yep, you're good.
All right, so I've heard that you can't really observe dark matter in any way except for through how it affects other objects in space through gravity. I was curious, is there any other actual evidence supporting its existence, or like what else is there?
So there's many different astronomical observations that do support dark matter. One of which I kind of mentioned, it's the spinning of galaxies. So if you're on imagine if you're on an old merry-go-round and you're going really fast and you're about to fly off. Matter, the gravitational force is what holds things together. So when that stops things from flying apart. So people studied, looked at the velocities of stars, how fast stars were spinning, and realized that galaxies aren't flying apart. So there had to be a lot more matter holding them together, providing that gravitational force. That's one observation. Another is seeing how light bends as it travels through space. And we know that matter has a gravitational effect on light. And so Einstein taught us that. So those are two observations that we call that indirect evidence for dark matter. And that's actually what we're looking for at SNOLAB, is the direct evidence of dark matter. So we're looking for a dark matter particle, a certain candidate called a WIMP, to bounce off the nucleus of one of the detectors, one of the materials inside the detectors that we have. So the two experiments that I talked about actually use two different techniques. So one is filled with liquid argon, which is a noble element, and one is filled with essentially freon, like a refrigerant, what keeps your refrigerators cold. And so whenever you expect the dark matter particle to bounce off the nucleus and make a very small amount of light or a very small bubble, and so that our detectors can see that light and measure that bubble and hope to find dark matter. So there's a number of experiments all over the world looking in similar ways with different materials. Xenon is another popular, another noble element to look for the dark matter interaction. So what we're looking for is for it to bounce off. So there's a lot of evidence that we should see something, but we don't know exactly what we're looking for. So having as many minds thinking about this problem and trying to come up with how to build the next better detector is actually what we're looking for too.
Cool. So in short, like we've only discovered dark matter through indirect evidence so far, but we're doing everything we can to find direct evidence of it?
Everything we can.
Excellent. All right. Very cool. Are there experiments in the works that might give us insight in the next couple of years?
So right now, a lot of what we're doing is scaling up the technologies we know how to do. We're also looking for better materials, cleaner materials to fill those detectors with. At big accelerators like the LHC in Switzerland, they're trying to see, can we create a dark matter particle in our collisions and look for it that way? There are some other theories on what dark matter could be. And so there's other experiments in a whole different vein also looking for it. We think we keep narrowing down the last, space of where we think it could be, how big we think it could be, and how interactive we think it should be based on all of our theories so far, that if we don't find it soon within the next decade or so, as you guys are growing up to be scientists, we have to come up with some new ideas. It's actually it's an exciting time in that way.
So there's your take-home lesson to all the classes. Discover what dark matter is by the end of the day. Good luck. We've got a sixth class. So Miss Huff's class, I know you guys have just been pouring in the last little bit. If you guys have a question, I know you weren't here for a lot of the presentation, but about what SNOLAB does, you're welcome to and go right ahead.
I'm not sure if they have any questions because they just came in, but I have one, and you maybe can kind of summarize it. Why are you researching dark matter underground? Is it because it is unsafe to do it up on the Earth's surface, or what's the reason that the dark matter research is happening in SNOLAB, a mile and a half down underground?
So it's the same backgrounds for the neutrino experiments. It's cosmic rays is how we call it, but it's just high energy particles that would interact in our detectors are stopped by the Earth. But the dark matter particles and the neutrinos aren't stopped by almost anything. They don't really see the Earth as an obstacle the way that we see things. They could just fly through your hand. Solar neutrinos, neutrinos produced in the sun, 100,000 of them fly through your thumbnail every second, depending if I'm here underground or you're there on surface. So many of our backgrounds would be stopped by the Earth, but the signals that we're looking for are not stopped by the Earth. So it makes it just cleaner detection.
Cool. Before we go through another round of questions with the classes, I just want to note too, so we've got 4 groups watching online on YouTube Live. If you guys want to type in questions in the chat bar on the right of the screen, I can pass them right on to Dr. Caden. So please do that. But yeah, let's head back to Miss Godard's class and start another round of questions. And you guys are demuted. You're good to go whenever you're ready.
How does the completed experiments that SNOLAB help the world?
I'm sorry, could you?
Yeah.
I don't think I quite.
How do the completed experiments that SNOLAB, that have been done, does SNOLAB help them? Is that the idea?
Like help the world.
How do they help the world?
Help the world. So that's a really good question, because a lot of our funding comes from public money. So what we do should help people. A lot of the techniques used at SNOLAB can be used for safety, for measuring the internal radioactivity of certain materials, so we can make safer materials, and we can make measure the materials that are coming across borders and make sure people aren't smuggling things in. In general, a lot of health cancer research has come from particle physics. The CAT scanners and the PET scanners for medical devices and proton therapy for helping fight cancer comes from particle physics research also. So that's another practical application of the technology that physicists have discovered.
Very cool. I think it's always worth noting too, is we do a lot of hangouts with physicists and we get this question a lot. A lot of physics is stuff that we have absolutely no idea how it's going to benefit us in the future, but things like GPS, communications technology, rockets, atomic energy, all of that has come about because of early developments in physics from hundreds of years ago in some cases that we just didn't have an application for, and then we found one later on. So
the internet itself came
right.
about because of particle physics. Particle physicists wanting to talk to each other and share information with each other.
So you can thank people like Erica for the fact that we can do this hangout right now. Cool. Let's go to Miss Leanie's group. Do you guys have a second question? Come on up.
Yes. Just wait.
You're good.
Okay. You can hear me?
Mm-hmm.
Yep.
Okay. How do you get the electronics? Because you said they have to get showered. How do you get electronics from the ground all the way down? Like, you can't shower, right?
Yeah. So
you have to do that.
we shower ourselves, and there's certain things that we can easily wash or wipe down, but we also have a lot of vacuum cleaners and really good clean vacuum cleaners to clean off the dust of things. And we also put things in plastic bags and layers of plastic bags in case our first ones break. So we clean things on surface, and then we bag them and carry them underground and then open the bag so they're not exposed to the dusty environment.
Cool. That'd be a great ad for like a home product over Christmas. Like, who needs Dyson when you can get the vacuum cleaners that help make SNOLAB possible? Right. Let's go to Mr. LeBeau's class.
We were curious, your specific research, what you're doing right now, and how that's contributing to your overall project. Like, how is your research being used?
So my role right now in the experiment is called the detector manager. So I help coordinate everyone who is running the experiment and all of the schedules of, should we put in a calibration device right now, or should we just take data? What are the threshold levels of which data should we be collecting? So that's part of what my main day-to-day work is. The research that I'm interested in, the particles that I think are the coolest, are the neutrinos that come from nuclear reactors and the neutrinos that come from the Earth itself. So we can use those to better understand why the Earth is warm. And the neutrinos from nuclear reactors we can actually use for nuclear safety. So we can, there's 3 nearby, relatively nearby nuclear reactors to Sudbury, and those are in Bruce and Pickering and Darlington, which are 250 to 350 kilometers away, but it's just at the right distance to measure some interesting properties about the neutrinos and verify some other measurements that there's some tension between different experiments. So that is one of the results that I am working on with other collaborators, and one of the useful things I think that we can do with my experiment.
Very cool. All right, let's go to Miss Huff's group. If I know you guys again came in late, but if you have any more questions from the class, from the teacher.
No, I don't. Sadly, I don't think. Not right at this moment.
Okay, we'll come back and check in before we go. All right, so let's go to Miss Russell's group. If you guys have a question, just come on up and demute. And we'll be good. Yep, you're good.
So how are you able to calculate the mass of said particle that you're working with?
The dark matter, you mean?
Yes.
So we can, we understand our detectors very well from our calculations and simulations and from previous work done. So we know that if a dark matter particle of a certain size and a certain interaction probability would hit our detector if it exists. So then we can say that since we haven't seen anything yet, we don't have a positive signal, we know that dark matter doesn't yet exist in this size range or this this interaction range. Right. So it's a bit of you keep looking for something and you don't find it, so you know it doesn't exist in the area that you had looked for it.
Before we take our last question from a class here, or our next last question before we start another round, we got our first question online, and I do want to encourage the large number of groups online to pass along questions there too. But is there any benefit to the lab being in Canada? Is there anything about the location up north, so to speak, that helps your guys' research, or is it a fluke of you know the mine being there to begin with?
So the original SNO experiment that kind of founded the lab, and the lab grew out after it, was based in Canada. Number one, because it used heavy water as the target medium for interactions, and Canadian nuclear reactors use heavy water to help in their reactor. So it was the largest source of heavy water to make the experiment work. And it is in Sudbury specifically because there is a mine here and a university with a good-sized physics department at the university. So having a mine, and the mining company was very willing to work with the community of researchers and let us have some of their space when they're obviously
busy.
So, yeah, they're busy, and science isn't their main focus, but they realized how cool it is to have a lab in their facility, and that there is a university nearby to have a base there as well to do the research.
Excellent, but there's nothing about the actual location that helps you guys catch neutrinos. I mean, other than being in the mine in Canada about catching neutrinos or dark matter, there's nothing there?
Nothing specific there other than being so deep helps us not have the other backgrounds. And the rock above us, the Canadian Shield, the norite rock, is very sturdy, stable rock. So there's not any worries of accidental cave-ins. This mine has been around for a long time, and it will continue to be. So we're actually also very lucky that the ore body is very rich. So there's not any worry that they're going to find all the nickel and close up shop and we're done science.
Excellent. But do you have time for another round of questions from the classes, Erica?
Yeah.
Great. Before we do that, a quick question. You talk about sort of going so deep underground and so far in. Has there ever been any accidents, any problems in getting to the lab, any things you've needed to, fix as you're taking people down? Nothing that isn't normal for mining. So Canadian mining is incredibly safe. There's outstanding regulations and a real culture and focus on safety and respecting all of the rules that makes it an amazing place to work, really. There's no, I'm not ever worried that someone's going to cut corners and someone's going to get hurt because of it. That being said, you hear the rock shifting and it sounds like a big pop. Sometimes that can shake your detector. It's not scary. It's just something you kind of get used to when you've been working underground for a while. There's sometimes that small things break, or there's always routine maintenance. So sometimes that interrupts your work day. But it's nothing out of the ordinary, and there's a real good feeling of everyone's working together to make things as safe as they can be, and everyone's taking the time to focus on that and to take the extra step. Great. I apologize. Let's go back to Miss Easton's class for another question. If you guys have any, just come on up and demute and go from there.
Hey there. So I had a generally simple question. I was just wondering, how could dark matter be used to improve humans or something in the future, like technology? How could dark matter be used to just improve on the society?
No question.
So I am not I don't know if we have any good ideas yet of how to use dark matter, but again, the technology that we have created to build our detectors, it has been useful. So one of the experiments here at SNOLAB uses what's called CCDs, or charge coupled devices, and they're the same thing that's in the back of any digital camera. These are the cells that actually record the pixels of light. Oh, I don't know if you just heard that. We just had a rock burst. If you heard a boom behind me. The charge coupled devices, the CCDs, they were originally developed for telescopes and the cameras inside telescopes that fly through space. And then we use them through our cell phones and cell phone cameras. And now we have bigger, better versions of the same device for dark matter detectors. Cool. I'm not sure if that answers your question completely.
We're getting there. We need to learn more about dark matter before we actually can.
We need to find it first, yes.
Yeah. All right, let's do a few more questions, guys, before we wrap up. So we'll start with Mr. Hari's class. If you guys have another one, there's so many of you. Come on up. And if there aren't, oh, yeah, cool.
Okay, so my question is, are you doing any experiments with animals? If so, why?
So that's an interesting question, because the particle physicists at SNOLAB are not doing any experiments with animals, but because of our depth, and there's actually increased pressure underground because there's more atmosphere and there's more Earth just on top of us. Excuse me, it's about 25% higher pressure underground. So you feel it as you're traveling underground, the same way that you would feel it in an airplane when there's decreased pressure. So there's two research groups that are studying, using the ultra cleanliness and the increased pressure, studying fish egg development and cell lines, looking for trying to make better cancer therapies and trying to understand how radiation affects cancer. And also one group studying fruit flies, using the fruit fly model to study how the increased pressure affects your metabolism. And that's really applicable to the mining industry, because people come underground every day for 10, 12 hours a day for the 20 or 30 years of your career. So understanding how the increased pressure over that time affects your metabolism, affects your health, affects your cognition, using the really well understood fruit fly model can help improve the safety and the quality of life of mining.
Excellent. That's actually a really good question. So how long are you in the mine in a day?
Our normal shift starts from 6 a.m. and goes until 4 p.m. That's the everyday shift that most people work. So that's 10 hours. So the underground crew at the lab normally does a Monday to Thursday or Tuesday to Friday schedule. As a scientist, I come down 2 or 3 days, maybe 2 days a week to help make sure everything is running smoothly. But again, since we're taking data kind of smoothly and regularly, less things need maintenance and construction. So I don't have to come down as often.
Yeah, cool.
Yeah.
All right, let's take 2 more from Miss Leanie's class first.
Okay, so what would be the consequences if...
Erica, Caden, 3321. Erica, Caden, 3321, please.
Okay, so what would be the consequences for your data and for your safety if a section of your lab were to collapse?
So it would be, if there was any indication that things would collapse, there's actually spaces in the mine that are have even more structure in the walls. So as they take rock or out of the mine, they then put other rock back in to fill its space so that things stay supported. And as I had kind of mentioned, the walls are really kind of bumpy. That's because they have this spray-on concrete. It's not just just sprayed on. There's also bolts that go into the walls, like 10 feet into the walls to hold everything together after they've removed the supporting rock. And then the concrete is just a nice seal on top of that. It's all very sturdy. But there's other areas that have even thicker supports, and those are what we call refuges, and all mines have refuges. So that's where we go in case there's any problems. Everyone gets called to refuge, and you sit there and wait until they've solved the problem and everything is clear and safe to go back.
Very cool. And I was going to do a couple more, but you were just called by the PA system, so I'll...
Nope.
You sure?
Yep.
Okay. Let's go to Mr. LeBeau's class then, and then we'll wrap up after that.
What classes should I take for a job at SNOLAB?
So you can study. You can study physics. Is what I studied. So I did my undergrad degree in physics, and then did my master's and PhD in particle physics. But we have a lot of people working at SNOLAB doing a lot of different things. We have engineers, so these are process engineers. We have mechanical engineers. We have chemical engineers. The whole lab staff, there's actually, there's a number of people who aren't scientists who we need to keep SNOLAB running. We have an IT crew, we have electricians, we have millwrights that all work on projects here at SNOLAB to help keep the lab running itself. We have chemists, but physics is a pretty great place to start. And this is really great physics, interesting physics that we do here too. And I really like particle physics because it's so hands-on. I like building detectors. I like taking data. I like solving problems. You see me with the big wrench. That's one of the things that I like most about working here is that you're actually on site building things. You're not just sitting at a computer looking at data that somebody else took.
Very cool. Actually, that's a perfect question to end us off with. So, Erica, what we do at the end of every Hangout is I'm going to demute the mic of every single class. So, boys and girls, if you guys could get ready and just join me in saying a huge thank you to Dr. Caden for joining us today. So, thank you so much. We loved having all the classes. Thanks so much for your great questions. Dr. Caden, that was great. Thank you for joining us for our first ever SNOLAB Hangout.
Pretty cool.
All right.
Thank you so much.
We look forward to having you back soon. And guys, have a wonderful rest